How's it going, everyone? Welcome to week 8 of the course. In terms of the checklist for this week, the first thing that you probably noticed if you've been in Mastering Engineering is about 5 people asked me for an extension on the homework that was due Sunday. I bumped that until next Sunday, but please try to get it done as soon as possible because if you're in the software, what you'll notice is that the second part of the Chapter 4 homework is now up. And I want to go and look just so I don't misspeak, but I believe it is 7 questions. Yes, that's correct. They really cover 3 different topics. First and foremost, how you compute the moment of a force about an axis. So in the first part of the Chapter 4 homework, we did a lot of computing moments of forces about points. In addition, this homework will look at your ability to compute the moment of a couple. And finally, it will look at your ability, if a bunch of forces are acting on a body, how you actually determine an equivalent force couple system, very similar to the example that we did in the actual lecture that was posted on Friday. One thing I wanted to call to your attention, remember we're getting the lectures up a little bit later in the week now. So usually they are posted at latest by Wednesday and Friday. So if you didn't get a chance yet, go back and make sure you watch this Chapter 4, Part 4 lecture. It has some example problems that will be helpful for you as you start to work that homework. In addition to the 2 homeworks this week, note that the first lecture of the week, which will get posted tomorrow, is going to review a subset of those new problems from Chapter 4. I'm probably going to pick 3 or 4. So if you're starting on the homework tomorrow morning, tomorrow would be Wednesday. If you want to hold off before you finish any particular problem, just to see if I'm going to do that as an example, feel free. But always best to try to work the homework problems by yourself, because just like last time, when we have the next exam, which will probably be in 2 weeks, covering chapters 4, 5, and 6, I'm going to take problems directly from the homework and the practice exam. The second lecture of the week, we'll move into chapter 5. That is just equilibrium analysis of rigid bodies. So we're going to relax that assumption that all of the forces pass through a single point on the body, making it a concurrent system, which can be modeled by a particle. Now we're going to say that in order for bodies to be stationary, not only do the forces have to be balanced, but also the moments. And what that means is that the body will neither translate nor will it rotate about a point. So we'll find that this chapter 5 is going to be pretty easy as long as we're comfortable with the chapter 4 stuff. So again, we're moving to an exam in about 2 weeks. So please make sure you're keeping up with the course as best you can. The one thing that I still owe you as well is kind of the extra credit planned opportunity for the first exam results, and I need to post those corrected scores based upon looking at your handwritten work that you submitted. So don't think I'm being lazy about that. You can kind of see my clock here. It's 8:19 at night, and unfortunately I started at 5 a.m. this morning and don't feel like I got anything done, but I did actually do a lot. It's just we have way too much to do this semester. So one of the emails asking for an extension asked me to review problem 4.2. So if this is all simple to you, feel free to just turn the video off now. However, I did want to go about it. We have a beam. We have 3 forces acting upon a beam, and we're asked to compute the moment of each force about B. So let's actually see how that would work. And we can do this all using a scalar approach. Remember that in a scalar approach, there's kind of 3 steps. The first thing that we want to do is determine the corresponding sign of the moment, because remember, in a coplanar or 2-dimensional system, the directions of all the moments are either going to be out of the plane or into the plane. So rather than talk about plus k hat or minus k hat, we describe the direction of the moments by counterclockwise rotation if the force induces a counterclockwise rotation, or a clockwise rotation. And the way that I said it was easiest to do that is find the point about which you're computing the moments, which is B, actually pin your drawing there, and then pull the body down in the direction of the force. And just look at the direction that your paper will rotate. So naturally, the rotation that's caused in that case is counterclockwise. And remember, we called counterclockwise rotation positive. In addition, sketch out your line of action and ask yourself, from the point of interest, what is the perpendicular distance from the point to the line of action? So there's an infinite amount of lines you can draw from point B to that line of action. However, only one is perpendicular. It's directly along the beam, and you notice it's 5 feet plus 6 feet away. So the perpendicular distance here is going to be 11 feet. And that the magnitude of the force, of course, is just going to be 375 pounds. So when you compute the moment associated with that second force about point B, it's going to be positive because it induces counterclockwise rotation. The perpendicular distance is going to be 11, and the force magnitude is going to be 375. So we'll just say it's 375 times 11, and this will just be in foot-pounds. So whatever that turns out to be, but it'll be a positive quantity. Let's talk about F2 for now. If you notice F2, it's not going to be quite as simple because it has both a horizontal and a vertical component. So let's, if we just kind of sketch out the way that that would look, right? We have the original force kind of going off here. at an angle. It has a downward y component and an x component that goes to the left. If this is 500 pounds, the way that we can determine the y component, and I'm not going to show all the steps. I usually like draw an equivalent triangle and actually find the sine and cosine of theta. But hopefully by now you know that if you want the y component, it's just going to be this side length divided by the hypotenuse. So it's just going to be 4/5 of that. So it'll have a magnitude of 400 pounds, and the x component is going to have a magnitude of 3/5. So that's just going to be 300 pounds. But what do we notice about this x component of the force? Notice if you actually draw this at the point of application, that's the x component and that's the y component. That line of action of that x component goes directly through B, right? So note that the x component will not induce rotation about B because its line of action is through B. However, the y component will. So if you look at the y component, notice that for F2y, let's do the same type of procedure. Pin it at B, pull it down in the direction of the y component. Notice that you get counterclockwise rotation. So for this component, the direction is going to be counterclockwise, which is actually positive. The perpendicular distance from the y component to point B is actually just going to be 5 feet. And then the force magnitude, as we mentioned, you need to decompose that 500-pound magnitude of force into the y component. So it will be 400 pounds. So for the moment associated with F2, which is just going to be associated with the y component. Why did I write, that should be a 1 here, sorry. It's going to be positive 400 pounds times 5 foot, so that would just be 2,000 foot-pounds. And then for the final F3 force, it's going to be a similar idea to what we talked about with F2. Notice you can write it in terms of a y component and an x component. However, the y component, its line of action, will also pass directly through point B. So if you actually extend that line of action of the y component out of this force, notice that it goes directly through point B. So the only one that you need to consider is the x component. So how would we actually do a decomposition of the x component? Well, notice that that x component is going to have a magnitude of, if you actually show your decomposition here, notice that relative to the angle you have, which is 30 degrees, the x component is opposite. So it's going to be 160 pounds times the actual sine of 30. And if you do your math there, you'll see that that is 80 pounds. So the little bit of tricky part is, how do you actually, for the x component, so I'm actually going to draw it out here. If I pin at B and actually pull to the right, notice I also get counterclockwise rotation. So for this x component, the sine is going to be counterclockwise positive. The perpendicular distance, what will that be? Well, think about it. Notice that if I draw the line of action of this force, it's in the horizontal direction. So from point B, it's actually the width of the beam that is the perpendicular distance. So 0.5 feet. So for F3, the only component that actually contributes a moment about point B is the x component, as we mentioned. It induces counterclockwise rotation, so that's positive. The magnitude of the x component is 80 pounds, and the perpendicular distance from the point of reference to that line of action of the x component is 0.5 feet. So this will just be 40 foot-pounds. So the question that someone asked me in email is explaining why these signs were negative, and in fact, they're not negative. Each of those vectors that contributes to rotation will induce about point B a counterclockwise rotation, so they all should be positive. So you actually could sum them up if someone were to ask you what is the total moment of that entire force system about point B. But we were only asked to actually report the individual moments of each force. So if you still have any questions about that, you know who you are. If you ask me, feel free to shoot me an email and I'll try to explain it to you in more detail. But I'm assuming that a good chunk of you found that problem pretty straightforward. It's kind of a good barometer. It's not a bad exam question to ask, because it's one of these that there's certain questions you can ask people in a class like this that is a transfer-based course. You can kind of tell if someone is having difficulty solving them. it will be very hard to pass them on to the next class. So there's going to be some questions on the test that are like this that are going to seem like really, really simple, but I've intentionally chosen them because they're kind of a good like binary barometer. They tell me whether or not you're ready to go on to the next class. And this is definitely something that you're going to have to be able to do to move on to dynamics, to be able to understand how to compute moments in a coplanar force system and how to spot when a force has a component which has a line of action that goes through the point about which you're computing the moment. And in that case, it will not contribute to rotation about that point. So the moment will be zero. So I will see you all in the first lecture video of the week. Have a good evening.